Welcome back to Textbook Toonz. Our journey today begins at the 10th century Parshvanath Temple in Khajuraho, India. Every figure carved into this intricate facade shares the space with an underlying mathematical logic embedded directly into the stone. This 4x4 grid is the Chautisa Yantra. In Hindi, Chautisa means 34, defining the entire matrix. Every row, column, and main diagonal adds up to exactly 34. The 4 outer corners also equal 34, as does the central 2x2 block. Ancient architects used these static geometric constraints to encode harmony into their buildings. But what happens when we apply these same numerical rules to the movement of sound? We find the answer in the ancient study of poetic and musical rhythm. In this tradition, scholars analyzed the mathematics behind every spoken sound. In Sanskrit and Prakrit poetry, every sound has a strict weight. Syllables are classified as either a 1-beat short note or a 2-beat long note. Around the 8th century CE, a scholar named Virahanka looked at these rhythms and asked a question: how many different ways can you fill a specific length of time using only those 1-beat and 2-beat syllables? For a 1-beat rhythm, there is one variation. 2 beats allow 2 variations. 3 beats can be filled 3 ways, and 4 beats give exactly 5 combinations. Virahanka discovered that for any length, simply add the previous 2 totals together. This generates the sequence 1, 2, 3, 5, 8, 13, 21, and so on. These are the Virahanka numbers, recorded over 5 centuries before the same sequence was identified in Europe. By applying a single additive rule to the constraints of a drum beat, Virahanka revealed a pattern that expands infinitely. We can analyze this sequence using parity, the odd and even properties of each number. Tagging them reveals a rhythm: odd, odd, even, odd, odd, even. This happens because adding 2 odd numbers always creates an even result. Since every third number is the sum of 2 preceding odds, we know the parity is any term instantly. Without doing any math, we can predict that the 20th term must be odd. Understanding these abstract properties allows us to predict the behavior of an infinite sequence without needing to calculate every individual step. These exact same underlying numerical properties govern the physical growth of the biological world right outside your window. A wild lily consistently grows with 3 petals. Buttercups bloom with 5. More complex flowers, like the daisy, produce dense petal counts of 13, 21, or exactly 34. If you look at the head of a sunflower, the seeds rotate in opposing spiral pairs that match consecutive Virahanka numbers. You can find the same geometric distribution on the scales of a pine cone. The additive rules ancient poets used to time their verses are the same rules governing how plants organize their physical growth. Now, let's take these sequence patterns and apply them to a specific challenge from your textbook. Angon is standing at the bottom of an 8-step staircase. He is only allowed to move up 1 step or 2 steps at a time. In how many different ways can he reach the very top? Use the musical beat derivations we explored earlier to map out the possibilities for this staircase. Calculate the sequence, find your answer, and post it in the comments. Join us in our next episode as we take these logic skills even further to solve cryptorhythms. See you there!